Let's take a look now at exercise number 70, a rational function where y is defined to be equal to 1 plus 5x minus 2x squared divided by x minus 2. And as in my previous video, we will walk through the key points that are listed in this section in the order they're listed. Again, the precise order doesn't really matter, but there are certain things that are easier to do before or after others. One of the first things we should generally look at is the domain, because this governs what x values we can consider in all the rest of our analysis. So we should see where this function is even defined. With a rational function like this, we have a polynomial divided by a polynomial. Polynomials are defined on all real numbers. The only thing we'd have to worry about is possibly division by 0. So we would need to consider where the denominator is equal to 0. That's a relatively simple equation to solve. We can tell that x needs to be non-zero. So if you were writing this, if you were required to state your answers in interval notation, then we could say that this is the interval from -infinity to 2. When I say x is non-zero, x is not 2, is what I meant to say. I don't recall what I actually said. X has to not be 2 so that we're not dividing by 0. So we have this interval from -infinity to 2, union with the interval from 2 to infinity. When we're doing things like where is it increasing or decreasing or whatever, I will often list intervals separated by commas because those are separate things. But the domain should be a single set of all of the x values for which this function is defined. So we want to take this set and join them together, and that's what this union operation does. It combines these two sets into a single set. The only real number not included here is 2. If you are sufficiently comfortable with set notation, and there are no restrictions that require you to use interval notation, you can write this in other ways. Right? You could use set builder notation. We could say that this is the set of all x, such that x is not equal to 2. You could optionally put an element, you could optionally write element of r in here if you wanted to be clear that we're talking about real values x, but in this class we're only doing calculus on real numbers, so we can, if we don't constrain x, we understand that it's real. Calculus on complex numbers is much more complicated. That is a later class. Or maybe you've taken discrete or something similar and you've done a little bit of set theory. You might say, okay, well, we have the set of all real numbers, but we need to subtract from that the singleton set containing 2. So if you know about set differences, you might do something like that. Don't get too ambitious. If you write something that has incorrect notation, that is bad. And will likely cost you credit. So play it safe and stick to whatever notation you're most comfortable with. If that is interval notation, use it. Whatever you have the best chance of writing correctly. But however we write it, the idea here is that the domain of this function is all real numbers except 2. Let's next consider intercepts. Again, the y-intercept is usually the easiest to find, because that is where x is equal to 0. So if we have our function defined explicitly, not implicitly, but explicitly, then we can simply plug in 0 for x and see what we get out for y. In this case, all those terms zero out. We have 1 over -2, giving us -1/2. So there's our y-intercept. X-intercepts are going to be a little bit trickier to find because we need to figure out where this function is equal to 0, and that will happen when the numerator is 0. And it's a little difficult to see how to factor that, right? If you think about the factors of the leading coefficient and the constant term, those are not going to combine in a nice way to give us 5 in an obvious, like, reverse FOIL kind of situation. So we don't expect this to be factorable over the rationals. We can check this to see if we have any real zeros. Let me go to another page here. So let's consider the question of taking 1 plus 5x minus 2x squared equal to 0. Using quadratic formula, the discriminant would be b squared minus 4ac, which looks like 33. So that means that our x values would be -b plus or minus the square root of 33 divided by 2a, so that's a negative 4. We have a negative here, and positive or negative there. So let's go ahead and take out that negative just to clean things up a little bit and say that this is 5 plus or minus the square root of 33 all over 4. So those appear to be the x values that are zeros of the numerator. Neither of those are equal to 2, so that means that these are both points where the function is defined and equal to 0. So we have x-intercepts at 5 plus or minus the square root of 33 over 4, comma, 0. Because, of course, on the x-axis, y equals 0. When it comes time to graph these, it'll be useful to have some sense of where this is, right? We can estimate, if we don't have a calculator on hand, we can estimate and say, okay, well, the square root of 33 is between 25 and 36, meaning the square root of 33 is between 5 and 6, closer to 6. So if we add these, 5 plus 5 point something, that'll be 10 point something, divided by 4 means it'll be a little over 2.5. We might estimate around 2.6, 2.7, 2.8, something like that. And it turns out that if we check this in a calculator, it does come out to be about 2.7. But like I say, with our mental estimate, we can get close enough for graphing purposes. And as far as the other one, well, again, this is between 5 and 6, closer to 6. So when we subtract, we get a number that is, we get a negative number that is smaller than 1 in magnitude. So when we divide that by 4, we get a negative number that is a little smaller than a quarter in magnitude, and indeed turns out to be about negative 0.2. A little bit closer to 0 than negative 0.25 would be 1/4. But like I said, even without a calculator giving us decimal values, and you note I'm not taking this to a bunch of places of accuracy. If you need to know exactly where it's crossing, then you can do additional work to figure out what those are. But we're moving toward just sketching a rough graph of this, so crude approximations are good enough. Which is why, like I said, if you didn't have a calculator on hand, just ballparking square root of 33 to be between 5 and 6, closer to 6, is good enough to figure out, approximately how big these numbers are. So let's go with that. That takes care of our intercepts. Symmetry. So symmetry, the types of symmetry that we've talked about in this section are even, odd, and periodic, related to reflectional, rotational, or translational symmetry. Looking at this function, it's a quotient of two polynomials, and we see that these polynomials involve both even and odd powers. So we do not expect to have any sort of symmetry of that type here. At least that's the simple types of symmetry. I'm going to write none. They're actually, one could argue that there might be a certain kind of symmetry, but not one related to the origin. So, we don't have to get, extremely precise about, is there some other point in the plane that we can rotate about? No, that's fine. This will work for us. We took care of the basics, and that's good. If you weren't sure, of course, like I did in the previous video, define this to be a function f of x, and then evaluate f of negative x, and take a look at what happens there as you simplify, and see if you either get the original function or it's negative. But here you should get a weird mixture, a hodgepodge of some terms being positive, some terms being negative, and it just won't work out terribly well there. So that's all we have there as far as symmetry is concerned. What do we have next? Asymptotes. So we'll first consider vertical asymptotes. Those are usually the easiest to think about, especially once we already know the domain. Vertical asymptotes usually occur at discontinuities. That doesn't mean that discontinuities usually have vertical asymptotes, but if you have a vertical asymptote, you're looking at a discontinuity of some sort. Rational functions are continuous on their domains, so the only place we could have a vertical asymptote is at x equals 2. Now, that could be a hole or a gap in the function. It could be a removable discontinuity. It doesn't necessarily have to be a vertical asymptote. So we need to check to see if this might be such a thing. If that is the case, that value making the denominator 0 would have to also make the numerator 0. But if you think about either factoring this, you can see that 2 is not a factor of 1, so the numerator as a polynomial does not have x minus 2 as a factor. Or you could just plug in 2 and see what happens. 1 plus 10 gives us 11, minus 8 is 3. The numerator is not equal to 0 there, meaning that as x gets really close to 2, we have a number that's close to 3 divided by a number that's close to 0. And you know that when that happens, we get a vertical asymptote. So we have a vertical asymptote. Vertical asymptote at x equals 2. Now let's consider asymptotes from n behavior. Maybe a horizontal asymptote. Looking at this, if you use shortcuts from previous classes, you might notice, oh, hey, this numerator has a higher degree than the denominator, so we expect this to have no horizontal asymptote. Using the techniques of chapter 2 and limits at infinity, if we divide out an x from everything, because x to the first is the highest power of x in the denominator, we would have 1 minus 2 over x, and then we'll have 1 over x plus 5 minus 2x. A lot of those terms go to 0 as x approaches positive or negative infinity, but we still have this minus 2x term that will go to positive or negative infinity. So again, there's no horizontal asymptote. But we might ask the question of whether there is a non-horizontal asymptote. Maybe we have a slant or oblique asymptote that is a diagonal line, or perhaps even a nonlinear asymptote. How would we figure that out? The easiest way with rational functions, when you have a numerator with higher degree than the denominator, what we should do with this is to do polynomial long division to find another way of writing our function. If we take x minus 2 and divide it into, and I'll rewrite this in descending order of the powers of terms, negative 2x squared plus 5x plus 1. Now, if you remember synthetic division, you could do that here, and that'll work faster, so feel free. But I want to remind you how polynomial long division works if you are a little bit rusty, because if you're dividing by anything that is not of the form x minus a constant, then synthetic division won't work, right? If you have an x squared in here, or some 2x, something like that, now suddenly you would have a lot more work to do if you wanted to use synthetic division. Polynomial long division would be the way to go there. So since this is more general, let's work through this. We ask we ask what do we have to multiply x by to get negative 2x squared? That's analogous to the regular integer long division question of how many times does x go into negative 2x squared. That's another way to phrase that if you want to be a little informal. We see that if we multiply by negative 2x, we get that. So we take that term and multiply by everything here. We have negative 2x squared. That becomes a plus 4x. Now we need to subtract this. And because of these mixed signs here, I think the easiest way to subtract a polynomial is to negate it and then add. Negative 2x squared plus 2x squared is 0. Those terms cancel as they should if we've done everything correctly. That was mainly written out as a check. 5x plus negative 4x leaves us a positive x. If you want to bring down what's left, you can. You don't have to as long as you remember that it's up there. Now we say, okay, x into x plus 1. Well, x times 1 is x. So we have a plus 1. 1 times x is x. 1 times negative 2 is negative 2. We subtract, negate, and add. We get 3. So we have, as a quotient, negative 2x plus 1 with a remainder of 3. And that means that our original function, y, is equal to negative 2x plus 1 plus 3 over x minus 2. Remember, this is analogous to if you do long division with integers. If you take 17 divided by 5, for instance, and you say, okay, 5 goes into 17 3 times, you have a 15, you subtract, you get a remainder of 2. That means that 17 divided by 5 is equal to 3 and 2/5, right? This means 3 plus 2/5. That's kind of the idea here. We have our quotient, negative 2x plus 1, plus our remainder of 3 divided by whatever our divisor was. In this case, x minus 2. So this is another this is an algebraically equivalent way of writing our original function. Y equals 1 plus 5x minus 2x squared all over x minus 2. We just write it like this. This makes it easier to see what the end behavior is. As x approaches positive or negative infinity, this part here, this fraction at the end, approaches 0, which means that the function in question becomes closer and closer to being negative 2x plus 1. Another way of saying that is that if we take y minus the function negative 2x plus 1, that difference approaches 0 as x approaches plus or minus infinity, right? Or you could write that as a limit. The limit as x approaches plus or minus infinity of this thing equals 0. So that tells us that this part here, the quotient, is our slant asymptote. Let's see where we are. Vertical asymptote is that. Slant asymptote is the line y equals negative 2x plus 1, was it? Yes, negative 2x plus 1. And you could see how we could get a nonlinear asymptote if the long division had given us a a quadratic or a cubic, for instance. That would be the function we write here, and you could sketch a dashed curve following that, and that would tell you something about how the rational functions graph behaved, roughly. Now, we might want to ask now something that is useful to consider when we have a horizontal or slant or nonlinear asymptote. Vertical asymptotes, we don't have to worry about this, but with any of those others, we might ask the question of, does our graph ever cross the asymptote? Right? Will this ever actually equal negative 2x plus 1? Well, if we look at this, we can see the numerator here is not 0. It never equals 0. There are no variables there. There's no x value for which this is equal to 0. So we can tell that that this function, while it gets very close to negative 2x plus 1, it never actually crosses it. Something else you could do is to look at the original function. You can go ahead and I'll just pop over to this one. We can look at the original function and try setting it equal to the asymptote, negative 2x plus 1. And if we try to solve that, we get 1 plus 5x minus 2x squared, multiplying both sides by x minus 2. That looks like negative 2x squared plus x plus 4x gives plus 5x minus 2. We can add 2x squared to both sides. We can subtract 5x from both sides. And we know that 1 is never equal to negative 2. This equation is always false. So our original function is never equal to the function we found as the asymptote, so it does not intersect. By which I mean that the graph of the original function does not intersect the graph of this slant asymptote. So that's good to know. Let's see. Next up, we want to look at increasing and decreasing. Those are based on the derivative of our function y. Now, looking at this expression here, taking the derivative is not too hard, but it does involve quotient rule. And then, of course, when we get to the second derivative, we have another application of the quotient rule. Let's instead look at this version of our function that we found here. If this is y, then y prime is equal to negative 2. The derivative of 1 is 0. Here we have, this is x minus 2 to the negative first, so we get, let's take that out, that would be minus 3 over x minus 2 squared. So that was a whole lot easier. Now, as far as figuring out where this is 0 or positive or negative, we might want to do a little bit more analysis with this, make it, maybe do a little bit of algebra to bring this together. This is negative 2 times x minus 2 squared minus 3 all over x minus 2 squared. You might be tempted to multiply this out. You can do so. It doesn't help a whole lot. Our concern here is to figure out where this thing is, where the derivative is positive or negative, right? So we can say, all right, well, where is it undefined? It's undefined at 2. But 2 is not in the domain anyway, so we know there's a discontinuity at 2. If we were to graph this thing, we'd say, okay, when x equals 2, this is not defined. Does this ever equal 0? Because that's where we could find critical points. You could distribute this out and take the quadratic that results, check the discriminant. You would find that the discriminant is actually negative, so its only zeros would be complex. There would be no real zeros. You can also look at this and realize that this is a shifting and transformation, I should say, of the usual quadratic y equals x squared. We see that the vertex is shifted down 3, and it also opens downward because of this negative 2 out front, which together means that this parabola, the graph of this, never crosses the x-axis. There are no other zeros. And in fact, this numerator here is always negative. The denominator is never negative because it's squared. So we can see that y prime is negative everywhere that it's defined. So the function is decreasing and decreasing. The function is decreasing on the 2 intervals on which it is defined, from negative infinity to 2, and from 2 to infinity. That also means that there are no extrema. Because the only place that could have been a critical point is where the function isn't even defined. There is no function there to be a maximum or minimum. On, to the left of 2, it's always decreasing. To the right of 2, it's always decreasing. There are no endpoints to include as possible extrema. So this function has no extrema. All that's left then is to look at the second derivative and consider questions of concavity. Coming back to this version, derivative of negative 2 is 0. We have a negative second power there, so it looks like we get a positive 6 over x minus 2 cubed. And making a little sign chart for that. Again, this is undefined at 2. But now we see that when x is greater than 2, this is positive, and when x is less than 2, this is negative. So we have concave down on the left and concave up on the right. Concave downward on negative infinity to 2. Concave upward on the interval from 2 to infinity, and no inflection points. There are no points of inflection here because the only place that the concavity switches is at a vertical asymptote where the function isn't even defined. So there is no point there for us to graph and see a switch. So I believe that covers all of the points asked about. Let's see here. X values of interest include 2, 2.7, negative 0.2, 0. So let's just make sure that our x goes from about, let's say about negative 2 to 4 maybe, and our y we can take to like, let's see here, if this is negative 2, 1, 2, 3, well, I didn't quite go to 4 like I was planning, but whatever, that's probably good enough. And let's see, for y values, we will need, we need to include the negative 1/2. There's not much else there. So let's just go ahead and call this... Oh, actually, we need to be able to graph this function y equals negative 2x plus 1. So let's give ourselves enough room in the y direction. Let's call this 5. And we'll call that negative 5 and just kind of see what happens. So we have like about a 1, 2, 3, 4, 1, 2, 3, 4. Just so we have something to work with. Oh, this is x. Now we had a y-intercept at 0, negative 1/2. The domain excluded 2, and we had a vertical asymptote at x equals 2. Oh, and x-intercepts at about 2.7 and negative 0.2, something like that. What else is going on here? The slant asymptote of y equals negative 2x plus 1. So that would intersect at about there. If we go right 1, it goes down 2. If we go right another 1, it goes down another 2. If we go right another 1, it goes down another 2. If we go left 1, it comes up 2. Left 1, up 2. So we have this diagonal line, just like we do in the other asymptotes. We can sketch that as being, with a dashed line there. So we have this diagonal asymptote and this vertical asymptote. We found that the function is decreasing both to the left of negative 2 and also to the right of negative 2. It's concave down here and concave up there. There aren't any extrema or any other, there's no inflection points or anything like that. So what we kind of have, and again, that was terrible, pardon the wobbliness from my tablet, kind of have something that'll go approximately like this. Smooth that out. It should not be at all wobbly. These should be smooth curves going like this. And that's the approximate shape of this graph. It does not cross the diagonal asymptote at all. The slant or oblique asymptote as it's called. I recommend that you take a graphing utility and graph the original function and also that diagonal asymptote as two separate functions and observe what happens. Play around with the viewing window to see that as you zoom out a bit, you should start to notice more and more that the more you zoom out, the more you should see that this curve is getting very close to that and very close to that as you zoom out and get a better picture of what's going on there. But that's the general idea there. Like I mentioned in my notes that I posted, probably the newest idea in this section is working with asymptotes that are not horizontal or vertical. But that largely amounts to, in the case of rational functions, it's fairly straightforward. You just do a long division and see what you get as your quotient, which is also consistent with how horizontal asymptotes work. If you have a horizontal asymptote and you do long division, your quotient will be a constant, and that'll be the y value that it approaches. So this isn't a completely separate thing. It just generalizes that and broadens it out a bit. But that's the rough idea of working through a graphical analysis of a function like this.